Hi. In this video I'll introduce the latest addition to my analog computer collection. This is the Electronic Associates PACE TR10. It's a little more sophisticated than the ComDyna GP6s I've been using in the past. Actually, the ComDyna GP6 has a few features that are an improvement over this one, but this is a more conventional industrial type analog computer. I purchased this unit a while back and have been slowly bringing it back to life. The seller mentioned that it was owned by a PhD student, and I assume eventually a PhD, named Vernon LaRoe, who was associated with the University of Michigan and the Willow Run Research Center. I did a little research and I found several of his papers online. I also have collected some of the newsletters from the Simulation Council. That was a group of, an industry group of analog computer users who met regularly to discuss the industry. And Vernon LaRoe was the chairman of the steering committee for the Midwestern Simulation Council. So he was known in the industry. I started with a cleanup of the unit. It apparently has been stored for quite a few years, probably decades. It was in pretty good shape, but there was a lot of dust and cobwebs and various debris inside. But all in all, the unit was mostly intact. I think as far as the electronics go, the only thing that was missing was one dial on one of the pots. On the initial startup, the unit appeared to be dead, which concerned me a little bit. Of course, trying to find a power supply for this would be very difficult. But I did a basic checkout. Of course, I checked all the fuses on the power supply and pulled out the power supply itself. It actually looked to be in pretty good shape. It, of course, still has the original capacitors, but the transformer and the capacitors all looked really good. I eventually opened up the control panel, which is the lower section there, and just found a loose connector. I suspect that came loose during shipping or possibly, during movement when it was stored over the years. But once I connected that, the unit came up really well. As you can see, the plus and minus 10 volt power supplies, which are used for computing, are within about 40 millivolts of their specified value, so that's only 0.4% off. It's pretty good for a unit that probably hasn't been turned on in 30 years or so. It's interesting, when I saw this on the site, I estimated it probably weighed about 30 pounds based on its size. But in its fully loaded configuration, it's actually a 93-pound unit. It makes it a little difficult to get it around, but luckily it's modular, so I was able to just simply remove all the modules, and that reduces the weight considerably. Then I can move the base unit around and reinstall the modules if I need to transport the thing. The TR10 itself is quite a bit different from the ComDyna GP6, which is the analog computer I'm used to. The ComDyna GP6 has fixed gain factors for both the amplifiers, the operational amplifiers, and the integrators. You can select either a gain of 1 or 10. With the TR10, those values are actually configurable. With the unit, I received some banana connectors, quite a good supply of those that are set up for the feedback resistors. And then there are also inline banana connectors that will set the input resistor. So depending on the ratio of the input resistor and the feedback resistor, you can set the gain of the individual amplifier. And the same with the integrator. The integrator is effectively the feedback component, and then by selecting the value of the input resistor, you set the integration time. So this one is configured a little differently. It's maybe a little more difficult to set up, but that's just the other option for setting these up. Also, this unit does not have the repetitive operation that the Comdyna GP6 has, so it's only a single simulation or single solution run. There was an optional module, according to the manual, that would allow repetitive operation, but that wasn't included with this unit. I was a little surprised when I saw this. It was called the TR10, but if you look at, and we'll get into that in a little more detail, but there were 20 op amps in the unit, so I was curious where the TR10 came from. As I read the manual and brochures that came with this unit, I realized that the typical TR10, or the standard TR10, was only half loaded compared to this unit. So the TR10 actually came from the standard unit, had 10 op amps and 10 attenuator potentiometers, and then you could select the nonlinear elements depending on your needs. But this is a fully expanded unit, so it's got 20 op amps and 20 attenuator potentiometers and an assortment of modules that we'll get into later. Another nice thing with this unit was it came with a series of manuals. You see to the right there, that is the operating manual, which is very useful. It's actually a very good introductory manual for analog computing in general. I actually haven't seen this online. I've seen quite a few texts related to analog computing online, but I have never run across this particular manual. Unfortunately, I'm not sure who I would go to get permission to scan and share this manual, so it's likely under copyright, but since EAI is no longer in business under that name, I wouldn't know who to ask for permission. Some of the manuals and literature that came with the unit were a full brochure, the operating manual that you see next to the computer, which actually includes a very detailed description of simulating or solving the equations for an automobile suspension system. So I'll probably run through that in a later video once I get the unit up and running. It also actually had two maintenance manuals. One had the old large format blueprint style drawings, and then another unit had just B-size drawings for convenience there, but effectively they were the same manual, but that's a very useful unit. Additionally, there was a full manual on the operational amplifiers themselves. So in the bottom row there in the green and red are the operational amplifier modules. Each one is a dual op amp with a chopper stabilization, and there's a full detailed manual included for those. There was also a digital voltmeter manual. Of course, there was no digital voltmeter included with this unit, but apparently that was part of the equipment, likely at the University of Michigan or at Willow Run, so that was included with the rest of the literature. Next, I'll take a brief look at some of the specific computing elements of the computer, and we'll zoom in for that. Across the top row are the attenuator potentiometers. Each module has two potentiometers. One is a single-ended with one end grounded, and the other is a dual-ended, so you could either ground one end or apply a voltage to either end, so that offers more flexibility. These are what I might call the deluxe model. I don't recall the model number offhand, but these have a push-button switch which tie the potentiometer into the null meter that I'll discuss later, which affords much easier adjustment of the potentiometers. There was a less expensive model of the potentiometer modules that would require a jumper lead down to the meter, so that would be quite a bit less convenient. And I've tested one of the modules, and it's working properly. It's interesting, I'm not sure why, but there are three different types of potentiometer modules here. If you look to the right, you can see the dial potentiometers. So those are actually convenient because they have a numerical dial. So those you could set strictly with the dial for a percentage of full scale. The two modules to the left of those have a different type of pot than all the other modules, but they actually have the same part number. So I'm not sure if that was just a later module or if it was an upgraded module or something to that effect. I won't go into much detail in this video. I think in a later video I'll show the innards of that. It's actually relatively simple. There's just the potentiometers themselves, the switches for switching the voltage down to the adjustment meter, and then the interconnect itself. I've actually gone through those, and some of them were seized up pretty good, but I think it was just due to some kind of something material congealing inside there. At first I was afraid maybe they were bound up, but just a little clean with alcohol, and they seem to be coming together pretty well, and they all adjust really nicely. There's no noise or anything on there, so I think we've got a good set of pots there. In the row below that are what are referred to as the nonlinear modules. So the first I'd discuss, or the most obvious of importance in an analog computer, are the white modules there. Those are the integrators. Each one is a dual integrator, and then it has the relay inside to be able to set initial conditions and then switch over to run mode. The rest of the modules I won't go into much detail. It's kind of interesting. I'm not sure what Dr. LaRoe was using this analog computer for, but he has several multiplier modules and at least 2 x squared modules. So those are what they call diode function generator modules. They're kind of interesting in and of themselves. I'll probably do a video on those separately and get into how those work, but they use a function called the quarter square multiplying concept that I'll get into. And then there are also what they call multi-modules, which are really just a jumper block. So if you need to bring a particular voltage to more points and you run out of connectors, you can simply bring it up to those, and then it's just a 4 binding post terminal block effectively. And there are, associated with some of the modules, I think just for convenience, there are power supply or reference supply modules. So that gives you many points to tie into for the plus and minus 10 volt computing voltages. If it was me, I would have preferred to have more integrator modules. That's really expands the level of differential equations that can be solved with this computer. But it'll be interesting. I'm not sure what Dr. LaRoe was using this for, but there's some sophisticated functions that can be solved with the multiplier and squaring modules. So that'll be interesting to get into. In the row of computing elements below the nonlinear row are the op amps themselves. These are, as I mentioned before, each dual op amps. They have a single chopper relay that's shared among the 2 op amps, and effectively there are just 20 copies of the same circuit, 2 per module with 10 modules. So with this design, we use jumper blocks to configure the operational amplifiers themselves, and then bring in the required voltages through the attenuator patch panel, and the op amps have to be patched individually to configure them either as integrators or as strict op amps, or even as a function using those function generators in the nonlinear row. So those are pretty straightforward. I'll probably do a complete video on those and go over the manual. It's kind of interesting. These are an old discrete transistor op amp, of course, so this was before integrated circuit op amps. The Comdyna GP6 actually uses the LM741, which was an early IC op amp, but these modules are simple transistor op amps made with discrete transistors, which is why they're so large. Below that is the operator console, and it's very interesting, kind of straightforward, but instead of just having a strict straight digital voltmeter, which were very expensive in that day, they have null meters. So with the large pot next to the meter, we can set the voltage range we want from 0 to 10 in about 3-digit precision, and then you switch the selection mode to adjust the potentiometers, and effectively you just adjust the meter for 0 volts, and then the potentiometer is set to the same as the large adjustment potentiometer on the control panel. It's a little confusing these days. I think that was very common back in the 50s and 60s, but it takes a little getting used to, because you don't simply set the attenuator potentiometer for a voltage as read out on the meter. You adjust it for a null value with the nulling potentiometer set to the value you require. I did a quick test on that, and it actually works surprisingly well. You can be, well within 1% with your voltage adjustments on the attenuator potentiometers. I won't go into this in detail, but below that are basically the control knobs for the meter. One is a range knob, and then the other is a mode switch, so you can either set it to look at the pots directly. You can use it as a null meter to null out against a voltage that's plugged into one of the jacks just below the meter. Then you can also look at the op-amp outputs directly. And there is another position for balance, which there are a set of potentiometers below the control panel to set the balance of each individual op-amp, which is required for accurate operation. It's not quite obvious, but the square gray field there, I'm not sure if you'll be able to see the numbers in the video. I can't see them on the camera monitor. But that is an overload indicator, and that's very convenient. On the Comdyna GP6, there's just a single overload indicator, so when the unit overloads, you have to determine which amplifier is overloading by switching through the various amplifiers. With this unit, if any of the 20 amplifiers goes into overload, number will light up, so it makes it easier to see where the source of the problem is. There is a knob below that gray field for the overload indicator that is an amplifier selector switch, and you can select any of the 20 op-amps as well as the reference voltages. So positions 21 and 22 actually select the output of the reference voltages, so you can verify that those are within spec. Then there is a rocker switch which sets the computer mode, and that initially starts out, if I recall, in the reset or initial condition mode. So in that mode, it sets all of the integrators that you're using in your equation to their initial condition. Then you would switch the rocker switch to run mode, and it will let the operational amplifiers run, of course. Then there's also a hold mode, so you can freeze operation at any time during the solution to check the outputs of the operational amplifiers. Just above the rocker switch is a toggle switch, which can be used to monitor the plus and minus 10 volt reference voltages. It's typically left in the plus 10 volt position for use with the null potentiometer. On the left side of the control panel, there is a separate panel with 4 dial potentiometers and 2 toggle switches. Those are used in conjunction with modules up in the nonlinear row to provide an extra 4 potentiometers with dial adjustments and switchable contacts, which I guess could be used to reconfigure the computer solution for different solutions. I haven't seen an application which required those switches, but they would probably come in handy. As it stands, the only way to monitor the computer output is through the analog meter. In operation, you can switch to any amplifier output and monitor the voltage as the solution progresses or when the solution is in the hold mode. Generally, since this is a single solution operation, it would be used with an XY plotter. Typically, you could use an XY plotter to plot one output against another, which would provide a phase diagram. Another option would be to use a strip chart recorder, which would monitor any of the outputs in relationship to computer time. So the strip chart recorder would be set to advance in computer time, and then the individual channels that would be monitored would be plotted on the y-axis of the strip chart recorder. I think that wraps it up for this video. I just wanted to give a brief introduction of the EAI TR10. I'll produce more videos going forward as I bring the unit up and demonstrate some of the modules and go through some of the circuitry involved in the individual modules. So hopefully I'll have another video out in the near future. Next, I'll put together a video demonstrating the basic operation once I get the integrator modules up and running. I hope you found that interesting, and thank you for watching.